Hi there. As you may know, the SAT Math is divided into two sections, the Math Non-Calculator and the Math Calculator. We'll be taking a look at the latter today.
We'll show you how to smartly use your calculator and avoid using your calculator to have you mastering the section in no time. If the calculator section continues to give you difficulties after we're done, consider upgrading to Testive coaching.
Let's get started.
This first problem has a lot going on at first glance, so we're just going to try to make sense of it by reading the problem. David invests $5,000 in an account that earns 3.0% compounding annual interest, where the value, V, can be modeled by the equation V equals 5,000 times 1.03 to the power of t, where t is the number of years. Which of the following graphs could represent this function? Okay, so this is a formula I'm unfamiliar with. It's not like a formula to have memorized. It's just given to us in the problem, and we have to figure out which graph could represent the function that we just read about. So I'm just going to make a note here that V is the value of his money. So V is the value, and that's going up this way. And in all these graphs, it looks like t is time, so it's the number of years, and it's going this way. Okay, so the first thing that you might think when you see a problem like this, depending especially on what math class you're taking right now, is, well, okay, I have a graphing calculator, I have a formula, and I have a bunch of graphs. Let me see which one matches by plugging the formula into my graphing calculator. So you would come over to your graphing calculator and you would put in, well, you don't have V and T, so you'd have to figure out that V is along the y-axis, and then put in the formula with y equals 5,000 times 1.03 to the power of t, I guess, not x, and then see what your graph looks like. See the shape of your graph. It looks like this. Okay, so now you've done that, you've put it into your graphing calculator, you come back over to the problem, and I kind of skipped over like figuring out, we had to make the note about V and T, which is which, substitute that in for X and Y into the calculator, and now we look back at our options, and we can see that two of them look like they could potentially match. They have the same kind of shape as the graph that we just saw. However, can't really be sure just based on what we just plugged into the calculator as to which of these matches, because we weren't able to control for t in the calculator, just plugging the formula in on its own. We didn't control for t being the number of years, which is always going to be positive. So our graphing calculator actually went like way negative because it starts, with infinite values of t. This problem is actually an example of a problem where it's on the math calculator section, but it's easier to solve without using a calculator if you just kind of make sense of what the formula is doing by thinking about the variables. So t is the number of years. It's always positive. It's always going up because time always goes forward, and it's in an exponent. V is the value along the y-axis. So what we're looking for is, if we know that this number in the exponent is always going up right here, then we know that as that number increases, well, what happens with exponents? As they increase, the value on the other side of the equation is going to go up more and more relative to the variable on the right side of the equation that's increasing. That's when you read about an exponential function. So if you think back to your very first algebra class, you probably learned this, and if you're in more advanced math now, you may have forgotten by now that you can identify these graphs kind of just by looking at them. So there's a couple we can rule out right away. We can rule out this one, because this is a linear function. The line is straight, which means that it's not increasing more and more as time goes on. We can rule out the first option, because in this one, the line is actually increasing less and less as time goes on. Eventually, it's going to flatten out. So that leaves this third and fourth one that we saw from graphing it, but we wouldn't have needed to graph it at all because now we know that we're looking for a shape that looks like this. We just have to figure out where it starts. Well, David starts with $5,000. So there's a clear right answer here because the fourth option shows David starting with $0, but he actually starts with $5,000. So this is going to be the correct answer, and it would be most quickly reached without using the calculator. As we go on through the rest of the lesson, you're going to see more problems in which using a calculator would actually be beneficial to you or might provide a little bit of a shortcut or a little more accuracy. First, we thought we would provide you an example in which you're told that you can use a calculator, but it wouldn't actually be the most efficient choice.
So here we're going to be discussing a glorified unit conversion problem. What makes this tricky, or seemingly tricky, is the fact that we're using these foreign units, this pace and hand. There are these ancient Roman units, but it doesn't really matter to the problem to know that they're ancient Roman. And the fact that this is given to you in a word problem, so you need to figure out what you want to do. So the key to finding the solution to this problem is see what we're given and what we need to find. So we're given a person who was 6 pace, and we're asked to find what is this person's height in inches. We are told that the hand is equal to 4 inches. So 1h for hand, of course, equals 4 inches. We're also told that 1 hand is equal to approximately 0.34 pace. So again, I'm going to write that 1h equals 0.34 pace. Now what I'm going to do is set up a series of conversions. You may remember this from your chemistry class. So if we start with 6 pace, you see that we don't have a relationship between pace and inches. We need to go from pace to a hand, and then from a hand to inches. So what we want to do is we want to multiply by a fraction where we have the unit pace in the denominator so that it cancels out. So what's our relationship for pace and hand? Because we've already said that we want to find a hand first. Or sorry, 6 pace and hand. So 0.34 pace is equal to 1 hand. So we set it up like this with the pace in the denominator and the hand in the numerator. And you'll see why we want to set it up like that in just one moment. And now the pace will cancel out and we'll have hands. And so we want to, again, put hand in the denominator now. You always want to put in the denominator what is in your numerator in the previous step. So 1 hand, and we want to get to what we want our final units to be, inches. So we say that 1 hand is equal to 4 inches. Now, again, these hands are going to cancel out. And we're going to be left with inches as our final unit, which is great. So then we just have to multiply across the numerator and denominator. So 6 times 1 times 4 over 0.34 times 1, and this is all going to be in inches. So before we whip out our calculator, let's simplify this a bit by hand to save some time. You want to smartly use your calculator and solve by hand where you can easily in order to save some time. Punching numbers into a calculator can be a bit cumbersome and time-consuming. Remember, the calculator is there to help you, not hold you back. So, of course, 6 times 1 is 6, times 4 is going to be 24. So that's very easy to do in your head. And same thing here, 0.34 times 1 is just going to be 0.34. Now this is where the math gets a bit complicated, and here is where I'm going to bring up our calculator. I'm going to go ahead and say that 24 divided by 0.34 equals, and here we're going to get 7.588 and so on. But if we remember correctly, we're asked for the number rounded to the nearest tenth. So we're going to go ahead and look at the 10th place, which is 5. We're going to look to the right of that. Say, is this number less than 5? Or if so, we'll round down. Is it greater than or equal to 5? Which it is. So we're going to round up. And our final answer is going to be 70.6 rounded to the nearest tenth. So here we're given a 5-gallon water jug that is then going to be split into smaller containers twice, into 2 other containers, and then each of those are split into 3. And then finally, we're asked to convert the smallest container after both of these divisions from gallons into pounds. So again, the key to these conversion problems is being aware of where you're starting and where you need to end. As if you were going on a walk and I guess didn't have Google Maps on you, let's say. So here we're going to take these 5 gallons and we're going to multiply by 1/2. You could also just say this is dividing by 2, of course, in order to divide this 5-gallon into 2 other containers. And then, after that, right, we're going to split it into 3 smaller containers, so multiply by 1/3 or divide by 3. And then, finally, what we want to do, don't forget to label your units, as I just have, we're going to convert from gallons into pounds. So we have gallons in our numerator right here. So we want, when we set up this conversion, based on this information given right here, we want to have gallons in our denominator so that it will cancel out with the gallons right here. So 1 gallon is going to be equal to 8.35 pounds. And when we multiply everything together, these gallons are going to be cancel out, and we're going to be left with pounds. So this is going to equal 5 times 1 times 1 times 8.35 in the numerator over 2 times 3 times 1 in the denominator. And remember, this is all going to be in pounds now, which is what we're looking for, because it says that right here. Right. So at this point, let's eliminate these ones, right, because they're not going to do anything, and save some time when we're inputting this problem into our calculator. And then let me grab my calculator right here. And I'm just going to punch in what we have, right? So 5 times 8.35 equals, let's save some time here. We know that 2 times 3 is 6, right? So, and then divide this number by 6. We're left with 6.958 and so on. We know that we want to actually get an approximate answer here because it asks for the approximate weight, as you can see right here. So we're going to round this to 7 and get 7 as our final answer right here. There is, however, a faster way to solve this problem. Since you know that it's looking for an approximate weight, and these weights are very different from one another, there's not a chance that you could round and get a number that was close to 2 of the answers. Since this is true, what you can do is you can round this 8.35 to 8, and everything else is actually pretty nice for multiplying. And then we would multiply 5 times 8 over 6 equals 40 divided by 6. Now, if you remember, 42 divided by 6 is 7, and 36 divided by 6 is 6. So that means that this number, 40 divided by 6, is going to be between 6 and 7. The only answer choice that is even close to between 6 and 7 is going to be this 7 right there. And once again, we can do this because it's asking for approximate weight. If it's not asking for approximate weight, use your calculator. And if you don't see this, that's fine, but we're showing you now so you can possibly save time on test day and leave time for other problems that might stump you more.
Here we have another problem where we're going to need to read it, find whatever pertinent formulas we have, figure out what numbers to plug in, and then probably do that on a calculator. The velocity of a tsunami as a function of water depth can be modeled by the equation v equals g times d raised to the power of 1/2, where g equals the constant of 32 feet per second squared, and d equals water depth in feet. If it's so what I notice already is that I have 2 of the numbers that are in my formula already defined. If a tsunami approaches a boat that is 250 feet offshore, where the water depth is 48 feet, what is the approximate velocity in feet per second of the tsunami when it reaches that boat? Okay, so there are a couple things to look out for here. One is that g is a constant, so that's already been defined. So when I have v equals gd to the 1/2 power, we're actually saying it's v equals 32 times d to the 1/2 power, because 32 is always going to substitute in for g. And d is water depth. So I see that I have water depth right down here in our problem. So water depth is going to be 48 feet. So it's actually going to be v equals 32 times 48 to the 1/2 power. I don't see a place to put this 250. And I think it might just be a number that's there to kind of lead me astray. I don't think I'm going to need to use that because I don't see a place in the formula for it. Because we're trying to solve for the velocity, which is v, and there are no variables left. So what I'm going to do is I'm going to come over to my calculator, and I'm going to plug in 32 times 48. Find what that equals, 1536, and then I'm going to raise that to the power of 1/2. So I'm going to hit this this here, raise the displayed value to the power of the next value entered. So I'm going to raise it, and then I'm going to make sure to use parentheses. 1 divided by 2, close parentheses, equals, looks like I get 39.19, a bunch of stuff. Okay, so if I come back over here, well, actually, I don't even have to go back to my other screen. I can see right through that one of my options is 39.19 feet per second. Okay, so that's going to be our correct answer. However, one thing that I want you to remember is that raising something to a fractional power is the same as taking some kind of a root. So raising something to the 1/2 power is the same as a square root. So if I raise 4 to the 1/2 power, really I'm just saying that that equals the square root of 4, which is 2. So in this case, I'm actually saying that v equals the square root of GD, or v equals the square root of 32 times 48. So rather than doing all of that x to the y stuff in the calculator here, I could actually just do 32 times 48 and then take the square root using the square root button, and I get 39.19, etc., and that is my correct answer. So actually I was able to check it two ways, but remember that something to the 1/2 power is just the square root.
One of the more common SAT calculator math problems is going to be a problem relating to probability. So let's go ahead and check this one out together and see what we can do. A magician challenges an audience member to a game in which he will roll a pair of 6-sided dice numbered 1 through 6. So this is just going to be your common dice. They're usually numbered 1 through 6. And as you know, when you roll each of these, you get a number at random between 1 and 6. And when you add these up together, because we're going to be measuring whether or not they will win on the ability to roll the dice so that the sum of both dice comes out to a specific number. So when you add these up together, so we want to get the number 6, it doesn't matter what combination it is. It could be 3 plus 3. When both of these dice roll together give you 3, or 4 and 2, etc., etc. The catch, however, is that the magician gets to pick the number. So the magician gets to pick which number these die are going to sum up to. So the sum is the number that they get to pick. The magician is aware of how probability works. What is the one number that he surely wants to avoid picking? Because it would result in the highest probability of the audience member winning. So we want a number that's going to be very likely to show up, and we want to avoid that number. That's going to be our answer choice. Well, we can make a list of all of the numbers that we could get from rolling the dice over and over. We could start with 1, 2, 3, go all the way up to 6, and just do this multiple times. The more efficient way of doing this is to organize that list into a sort of matrix here, where we're going to have a column of all of the results that you can get from rolling one of the dice, and then a row here at the top with all the results that you can get from rolling the other. Of course, that's going to be the same. You can get any number between 1 and 6. But organized like this in a nice little table, you can figure out which number shows up the most just from adding them together. This is a little bit like Punnett squares if you've done this before in your biology class. So let's go ahead and just figure out some sums. So 1 plus 1 is 2, 1 plus 2 is 3, etc., etc. You start seeing a pattern, obviously. 2, 3, 4, 5, 6, 7. And then for the next row, very similar. 2 plus 1 is 3, 2 plus 2 is 4, and again we have a pattern. 3, 4, 5, 6, 7, 8, 3 plus 1 is 4, 3 plus 2 is 5, again 4, 5, 6, 7, 8, 9, and we can already guess what's going to start happening, right? 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Now that we have it like this, we can go ahead and see which number of all of these shows up the most. So we see here that if we go across, 7 shows up 1, 2, 3, 4, 5, 6 times. Whereas if we go across any other way, we got, for example, 6, 1, 2, 3, 4, 5 times, or 8, 1, 2, 3, 4, 5. The only one that's going to show up 6 times is going to be the number 7. So there's more possibilities that the sum of rolling any 2 dice together will give you 7. So that number will have to be 7. Now, watch out here. We didn't use absolutely the calculator at all. And this is actually going to happen a lot in the calculator section. There's no need to use your calculator for a lot of these problems. And in fact, if you tried, just because it's a calculator section, maybe you think that it'll be easier for you to reach the answer using your calculator, doing anything in your calculator, maybe creating this table in your calculator somehow, you're just going to waste a lot of time. So sometimes the most efficient way to reach an answer is to not use your calculator. The following math calculator problem is going to require us to really understand what a 30-60-90 and a 45-45-90 triangle are and how we get to use them when we're looking at three-dimensional shapes. Just as a quick review here, when we have a square, like we do for this pyramid, and we take the diagonal of that square, we can generally assume that these are going to be 45, 45, and 90s. And that's because this 90 degree here at both corners across the diagonal is going to be split into 2. And we know that because it's a square, the remaining angle will be 90 degrees. So 90 divided by 2 is 45 on either side. And then we have 90 degrees here, so we know it's a right triangle. And we should know from what 45, 45, 90 triangles are, that they are going to exist in this relationship where one of the lengths of the legs, whatever that is, will also be the length of the other leg, and that the hypotenuse will be, the length of that leg times the square root of 2. Now, when do we ever see 30, 60, 90 triangles? Usually you're given an equilateral triangle where each of the sides measures the exact same, and because the inside angles of any triangle have to add up to 180, each of the inner angles has to be 60 degrees, since 60 times 3, and there's 3 angles in a triangle, equals 180. When we divide this by half, we're similar to what we did in the square there, going to divide that 60 degrees into two 30-degree angles, so that each of these halves becomes a 30, 60, 90 triangle. And just like the 45, 45, 90, 30, 60, 90s have certain properties, where the length of the shorter leg, which we can call x here, will tell you a lot about the length of the other legs, so of the other side. So the longer leg will be the same length as the shorter leg times the square root of 3, and the hypotenuse will be twice the length of the shorter leg. So this is very useful information, especially for this problem, because they're giving us, the only thing they give us here is what the height is. So this value here, h equals 3 root 2. That looks a lot like our 45, 45, 90 triangle. And why that's useful is because that can tell us a lot about this measurement here, EB, if we wanted to solve for that value. Now, we don't necessarily have to, but something that we can do is consider the diagonal of the square, which is, again, just the hypotenuse of a 45, 45, 90. We divide that by 2, since the height comes from the center. And doing that, we're going to get now a different triangle that we could try to learn something about and see if it relates to another one of our special right triangles. So let's go ahead and figure out what BD is, our diagonal. Well, we're told that this is a square-based pyramid, and that has an area of 36 inches squared. So in order for a square to have a base of area 36, the sides must be 6, since length times width would be here 6 times 6, which is 36. So if we're looking at the diagonal of this, we're going to have a 45, 45, 90 triangle that will have both side lengths of 6, and then we'll need to have a diameter or a hypotenuse that equals 6 times root 2. Well, if we're looking at height then as the height of our next right triangle here, this one here, BE to the center, I'm going to go ahead and call the center here O. And we draw a triangle BEO. We know then that because the height is at the center, that this is going to actually measure 3 root 2, half of the length of the entire diameter. And we were told the height already is also 3 root 2. So if we know that both of these legs measure the exact same, and that this is a right triangle, then this is also going to have to be a 45, 45, 90. So just like for the other 45, 45, 90, all we're going to do now is multiply these by the square root of 2 again. So we're going to get 3 times root 2 times root 2, or otherwise 3 times 2, which simplifies to 6. So remember, this is the length of BE. So if we look at BE in this triangle here, we can label that side 6. Now that tells us a lot. Remember, the base square already had side lengths of 6. So if we look at angle BEF here, which is this angle, it is part of a triangle that is, if you look at triangle AEB, that triangle is going to have a base of 6 and a side of 6. And we know that then because all the side measurements here are going to be the same, since this is a square, and we could have done what we did between BEO here easily between with any other corner of the square, since the diagonal is going to measure the same from whichever points you take it, from BD or CA, that this is going to have to be an equilateral triangle. So then that means the inner angles are each going to be 60 degrees. We're asked for BEF though, not for BEA or any other of the 60-degree angles. And here we need to know that, well, when we have an equilateral triangle that we divide by half, that's a 30, 60, 90. Because we're basically splitting that 60 degrees into 2 angles. So the measurement of angle BEF, which would be, I'm going to go ahead and write those letters once again here, is going to have to be 30 degrees, like the smaller angle of any 30, 60, 90 triangle. So the answer to this will be that angle BEF equals 30 degrees. And when they're asking for the measure to the nearest degree in a grid, you don't need to put in the degree symbol. Just go ahead and write in 30, and you should be good. Great. Today we looked at representative problems in order to discuss strategies on how to make the most of having a calculator.
Remember to always use your calculator wisely and never use it as a crutch. If you keep what we showed you in mind, you'll be on your way to acing the section.
Happy prepping!